We've been talking about oscillators in a very ideal situation when there's no damping force. So in other words, we're ignoring friction and air resistance. If I have this mass on a spring, and I'm going to hang it vertically because it's a little easier to show a graph of the y position of my mass as a function of time. And I take that mass and I pull it down until it's right here. And I let go of it at time 0. That mass is going to oscillate back and forth. It's going to go up through the equilibrium position to some position up here where it will momentarily come to rest, and then it will go down and it will oscillate back and forth between those two positions. If I plot that y position as a function of time, where am I going to start? I'm going to start out at negative a at t equals 0. And I know eventually I'll come back to that point. And it's going to oscillate between negative a and positive a. Our curve will look something like this. Always oscillating between negative a and positive a. But we know that that doesn't really happen because we have air resistance. And as that mass goes up and down, it interacts with the air, it loses some energy. So let's take a look at what this graph would look like if we include damping. In other words, if we allow our oscillator to lose some of its energy to the air. If we start with our object down here at y equals negative a, and we let go of it, it's not going to make it all the way up to y equals a. It's going to be a little short. And then when it comes back down, it's going to stop a little short of where it was on the positive side of the axis. Each time it oscillates back and forth, it's losing a little bit of its energy to the air, and it's not going to compress or stretch the spring as much. So then it's going to come up, and maybe it'll be here, and then it'll come down, maybe it'll be here, and it goes back and forth like that, until eventually what happens? Eventually it comes to rest at the equilibrium position of our spring. So let's graph that. With damped motion, every time our mass oscillates back and forth, the amplitude is reduced a little bit. The way you get that equation is you say the sum of the forces is equal to ma. And with no damping forces, what did we have? We had a minus kx equals ma. And a is the second derivative of x with respect to time. Of course, x is a function of time. And of course, I'm using x here as just a generic one-dimensional motion. It could be horizontal motion like we've looked at in the past, or it could be this vertical motion that we're looking at now. I'm calling it y here, but in the equation I'll use x. The displacement from equilibrium. If we have a damping force, some resistance with the fluid that our mass is moving through, and our mass isn't moving too fast, we can approximate that as a force that's proportional to the velocity. So I have to add a term here that accounts for that. So this was no damping. If we have a damping force, we're going to get the sum of the forces equals ma. We're going to get a spring force. And we're going to get this damping force, which is proportional, that's our proportionality constant, to the velocity, and it's opposite the direction of the velocity. When this differential equation is solved, you get a function that looks like this. So it looks very similar to our previous function, except we have this damping term, and our omega is slightly different. Now there are a number of oscillating systems that we can think about. One is the shock absorbers on your car. When you hit a bump in your car, you want the shock absorbers to absorb and compress and take up some of that energy. But you don't want your car to still be bouncing up and down halfway down the street, right? You want it to very quickly go back to their equilibrium position. So you wouldn't want the shock absorbers on your car to have a graph that looks like this. This is what we call an underdamped system. So let's think about the case with your car, or maybe a better example is a door with a spring that closes the door. So let's think about a door. It's got a hinge, and we're looking down from the top. Somebody walks through this door, opens it, walks outside, and the door stays open. We don't want that. We put a spring on it that wants to pull it back to the equilibrium position. But we don't want our door to slam shut. So we put some mechanism in there to damp the motion as it closes. Well, if the damping force isn't strong enough, what happens? The door still wants to swing back through its equilibrium position. We displace the door a little bit. We open the door. We let go. The spring pulls it closed, but the damping force is not enough. The spring actually wants to pull it through, not just closed. The door wants to go to the opposite side. Well, we don't want that. We don't want the door to slam into the door jamb. This is an underdamped situation. We need more damping to slow that door down and stop it before it hits the door jamb. Well, what could we do with our door and our spring? We can put a bunch of damping in. You push that door open, and instead of the spring pulling the door closed very quickly, the spring tries to pull the door closed, and there's so much damping, it takes forever for the door to close. 2 hours later, we're still waiting for the door to close. It takes forever. Well, that's one way to prevent the door from slamming shut, but that's not really ideal. You want your door to close in a more reasonable amount of time. That's what we call overdamped. We need critically damped. For the condition to be met for critical damping, the door is displaced, we let go, the spring starts to pull it back towards the equilibrium position, and it quickly slows down and approaches equilibrium in the fastest way possible without crossing the x-axis, without crossing the horizontal axis. So if it goes over, if it crosses this line, it's not critically damped. We want the displacement to go to zero as quickly as possible without crossing that horizontal axis. That's critically damped. And that's what we would want for the damping on our door, and that's what we would want for the shocks on our car. We want them to absorb the bump, the pothole that we drove over, but then very quickly go back to their equilibrium position. We don't want the car bouncing up and down as we're driving down the street. Damped oscillations remove energy from our oscillator and give it to the air or whatever the fluid is around the oscillator. Driven oscillations are a way to add energy to our oscillator by reaching in and doing some work on our system. If I have some mechanism for pulling up and down on that spring and trying to add some energy to the system, then my oscillations might get bigger and bigger and bigger over time. They might look something like this. So as we add energy, the oscillations become larger and larger amplitude. The response depends on the frequency that we're adding our energy. Just like when you go to the park and push someone on a swing. They're a simple harmonic oscillator. If you push them at just the right frequency that they want to oscillate at, their amplitude gets bigger and bigger and bigger. But if you push at the wrong frequency, sometimes you cause them to go a little faster and higher amplitude. Sometimes you break their motion and cause them to go slower, and you can't really get their amplitude to increase. So a lot of this depends on the frequency that you're pushing and the frequency that the oscillator wants to oscillate at. We call that the natural frequency of oscillation. And we can figure that out. For a simple pendulum, we know omega is the square root of G over L. So we know the frequency that wants to oscillate at. And if we add our pushes at just the right frequency, we can get the amplitude to increase and increase just like this.